Hello YouTube, Blue CFL here. Today I'm going to be doing a bit of an explanation on how direct current electromechanical horns operate. There's an AC one right over there, and we'll be taking a quick look at that a little later on. Right here I have a schematic diagram drawn out. It's very simple. There's no other type of components like diodes or capacitors that most horns have. This one's just the bare basics that a standard direct current horn needs to operate. The components: a normally closed switch between that dot and that dot. NC stands for normally closed. That is electromagnet. That's the diaphragm. It's just a horn symbol. And then you have the conductor, thrown by the straight line there. This broken line right here shows that there's a mechanical connection in between the switch and the hammer that is in between the diaphragm and the electromagnet. I didn't draw any type of hammer in there, or I probably should have. You have your positive terminal there and your negative terminal there. How these horns work is, upon activation of the system, the electromagnet will either actuate the hammer, pushing it either into the diaphragm or pulling it off of the diaphragm in the case of these wheelocks right here. We'll take a closer look at those later on. Now, actuation of the hammer would include the deactivation of the switch. This switch would open up once the hammer is actuated. And once the switch gets opened up, the hammer would move back into its original position because the electromagnet is no longer active. And now once the electromagnet gets back into its original position, that means the switch gets closed again, and current flows through, and the electromagnet would reactivate and obviously push the hammer back down into the diaphragm. Now this happens extremely fast, and that's what creates the sound you hear when one of these electromechanical horns activate. Now, I'm going to move that to the side there. It's magnetic, so it's not really going to slide much. I'm going to take a closer look at these to start off with. These this one's a Wheelock 7002, and this one's a 7002T. There's really no difference between the two other than that one's older than the other, and one of them has terminals. Now, the other difference you might notice is that this one does have its protector on it, and this one does not. I'm in the middle of repairing this one. Now, the protector is protecting that little switch. So you see that there are two terminals right here. Let this thing focus. I don't think it's going to focus that well. Yes, no, maybe so. But you can see the hammer right here. And you can see there's the mechanical connection, this line right above the hammer. It's going to go to the one lead of this switch and the other lead of this switch. And you can see that they're connected right now. And when the horn gets activated, you get this longer part right here gets pushed up, which would stop the circuit, which the hammer then would get pushed back down, and reactivating the circuit, and that happens extremely fast. And with 7002s and 7002Ts, that also plays into how the strobe operates, and I want to make another video about that later on. This obviously has the same thing under it. This is my Halon variant. Now this one works a little differently. This is an 895B-001. You have your switch right here. This one is also normally connected, but when this one, it's a lot of talking here. When the electromagnet gets activated, it would push up, and the other terminal is sort of under where this little dot is. And it would open up the circuit when the, pushed up. Yeah, maybe it does get pushed up. But anyway, yeah, it would get, it works basically the same way. They all basically work the same way in this case. Activation of the horn would open up this little switch here, which would turn off the electromagnet, and it would drop right back down, and it would reactivate the switch here, and it just happens extremely fast. Simplex 4051. Now, the switch is held right in this little circuit board here. I think one of the reasons why this is a higher pitch sound is because there's not as much of a space in between the switch. There's like a gap there when it opens up, and there's not as much of a space there. So that's why it's a higher pitch, and there's the same thing in between the diaphragm and the electromagnet itself. Usually the smaller the gap, the higher pitch the sound, because if things move at the same speed and there's not as much space for it to go, it's going to make a higher pitch sound. Now, comparing this to a 4050, 4050 obviously has the holes pre-drilled for such a switch, but it doesn't have the switch because this is an alternating current horn. Alternating current horns obviously do not need that switch because it is alternating current, and it uses the alternating current to produce the oscillation it needs to have the horn activate. That's why the sound is such a low pitch, and that's why most alternating current horns sound at the same frequency. At least in the US, they all sound at the same frequency. Pitch may be a little different due to the size of the diaphragm, size of the horn, amount of power it uses. But all direct current electromechanical horns from this era basically follow the same principle. There are newer ones, I believe from the 90s, maybe the 2000s as well, until they were discontinued, that actually had a small circuit board on here that worked as a timer. So they all basically had the same pitch to them, but it didn't really change the whole thing that it was the concept that you have a hammer that needs to tap against a diaphragm really fast to make sound. Anyway, that's me explaining how these pretty much work. It's not really much I can do to show a hands-on demonstration. It just travels back and forth really fast. Blue CFL, I'll be out. If you have any comments, questions, that's what the comment section is for, and I'll be happy to answer them. And hopefully to have a follow-up video at some point in the future as well.